My name is Caroline Colbert. I'll be sharing some highlights from the new JMRI publication, Estimation of Fractional Myocardial Blood Volume and Water Exchange using ferumoxytol-enhanced MRI. I'd like to thank the co-authors of this work for their contributions, and to acknowledge our grant support from the American Heart Association and the National Heart, Lung, and Blood Institute. In studies of myocardial perfusion, the measurement of fractional myocardial blood volume, which we typically define as the fraction of a voxel of myocardial tissue that is made up of the intracapillary blood volume, can provide insight into myocardial ischemia severity beyond what we can get from measurements of myocardial blood flow alone. Fractional myocardial blood volume can be estimated using magnetic resonance imaging with the iron-based contrast agent ferumoxytol. This technique has the potential to capture a hemodynamic response to myocardial perfusion during contrast steady state. In this study, we hypothesized that a two-compartment model of the myocardium can be combined with ferumoxytol-enhanced MRI T1 mapping to quantify fractional myocardial blood volume as a proxy for myocardial perfusion in a large animal model. We aim to implement and test a two-compartment water exchange model for quantification of fMBV, and to compare model-fitted fMBV to other approximations and abbreviated protocols for estimating myocardial perfusion. A two-compartment model of myocardial tissue typically treats the myocardium as being made up of two physical spaces, which correspond to two spin relaxation environments, the intravascular and extravascular compartments. Ferumoxytol, being a purely intravascular contrast agent, does not leak out of the intravascular compartment. However, unbound water is free to diffuse between compartments. The fraction of this hypothetical voxel that's comprised of the intravascular compartment and the exchange rate of water across the vessel wall both affect the MR signal of this voxel. Prior works have described in detail a model of the MR signal of this two-compartment voxel based on its fractional blood volume, water exchange rate, and other physiological parameters. When myocardial T1 maps are acquired over a range of doses of the contrast agent ferumoxytol, we can solve for the fractional blood volume and water exchange rate of the voxel using the two-compartment model. As a special case, when the exchange rate of water is sufficiently fast, the two-compartment model can be simplified to the expression here, and fractional blood volume can be approximated as the ratio of the change in R1 of the tissue and blood pool. In this study, we imaged 9 healthy normal swine models and a single swine model with an artificially induced single vessel coronary stenosis. We acquired short-axis MOLLI T1 maps at baseline and following 7 individual ferumoxytol infusions, ranging from a cumulative dose of 0.125 to 4.0 milligrams per kilogram. We used these multi-dose acquisitions to estimate fractional myocardial blood volume and water exchange using a two-compartment model in MATLAB. We then compared our blood volume to the fast exchange approximation of blood volume using Bland-Altman analysis. Finally, we used the Elastics platform to co-register our multi-dose T1 maps and perform a pixel-by-pixel fit of blood volume in order to generate blood volume maps in our healthy and ischemic swine models. To summarize our primary results, we found a mean mid-ventricular blood volume of 7.2% in our healthy swine models and a mean water exchange rate of 11.3 Hz. These values fall within the range of previously published results in human and animal studies using similar methods. For more details, take a look at the discussion section of the full manuscript. We found that while there is a significant variance in the baseline blood volume between swine subjects, we found no significant variance in blood volume between myocardial segments from the anterior to anterolateral segment in our healthy swine. When we compared the full model-fitted blood volume to the fast exchange approximation of blood volume in our healthy normal swine models, we found a moderate correlation between the two measurements. However, we also found limits of agreement that might be wide enough to obscure subtle findings in the clinical setting if the simple fast exchange approach is used. That means if fast exchange blood volume, which only requires two ferumoxytol-enhanced images to be acquired, is used instead of a full multi-dose approach like the one used in this study, it could potentially obscure something like a hemodynamic response to myocardial ischemia. Finally, our blood volume and water exchange maps in a single swine model with an artificial coronary stenosis in the LAD, which is shown here on an X-ray angiogram, shows a quantitative increase in pixel-wise blood volume in the anterior, septal, and inferior myocardial segments of this apical slice that are hypoperfused by the stenosed LAD. We've also shown mid-ventricular maps of blood volume and water exchange in a healthy normal swine subject for comparison. This result provides early evidence that blood volume measured using ferumoxytol-enhanced MRI may be able to capture a hemodynamic response to myocardial hypoperfusion during contrast steady state. Overall, from this study, we're able to conclude that estimation of blood volume using a two-compartment water exchange model is feasible when combined with MOLLI T1 mapping over a range of ferumoxytol doses. Blood volume has the potential to provide a unique means of assessing myocardial perfusion, especially in the setting of impaired renal function when the use of gadolinium-based contrast agents is contraindicated. And then, if confirmed in a patient study, fractional myocardial blood volume may provide a potential direct marker of tissue perfusion. Thank you.